Hello, welcome to the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is a little mini series on split plot design, and we're on part 2, and I'm going to call it Design Matrices. And I really encourage you to watch part 1 in model development. And so here we're going to introduce the design matrices of two types of split plot designs. One is called split plot completely randomized design. The other is split plot randomized complete block. So as a reminder, a split plot, there's two sort of randomizations going on. One is called the whole plot randomization that's applied to a larger experimental unit, and then each of those larger units are subdivided, split into different pieces, and another treatment is applied to each of those whole plots. So the first one is a split plot completely randomized design. And this is the model. So we have a factor, alpha effect, and the error associated with that first randomization. So if you were to look at this model here, you'd go, oh, that's a completely randomized design, and you'd be right. And then the second one, the second factor we're going to call gamma, and then there's an interaction between alpha and gamma, and then the error associated with that randomization. Often these errors are combined together in this faction. The whole plot error is normally distributed, the subplot error is normally distributed, they're independent, and then that epsilon is a combination of those two. And it can be generally written as y equals x beta plus epsilon, where epsilon is multivariate normal, mean zero, variance sigma squared times v. And so notice that in our previous designs, this has always been the identity matrix. So in matrix notation, we can write it as, this x can be broken up into a column of ones, the column associated with the first factor, the column associated with the second factor, and then the interaction terms. And so if we look at the design matrix, here's the column of ones, right? And in this vector here, the first piece is a mu. The next t parameters in this vector deal with the alpha coefficients. The next m parameters deal with the gamma parameters, and then t times m parameters there are associated with this vector. So here we have a column of ones. And now, remember, the first one is a completely randomized design. And so factor 1 is, there's r replicates, and there's times the m treatment. So it's a vector of ones associated with, level 1 of factor A. And then this is level 2 all the way to level t. So there's t columns. We call that x of t. Now within each whole plot, remember the whole plot is replicated several times here. So within a whole plot, there are m levels of that second factor, and then each gets a parameter. And then the next whole plot, and the next, so if we go down to the last whole plot, and then they each get it's the same parameter, but they each get their own parameter. And then this is repeated for each of the whole plots for the different levels of the first factor, right? And then the interaction terms, are just these, but you repeat them as you go down. So this is actually the design matrix. Now, this here, XW, which we're going to introduce, and it's going to be very important later, and it'll make more sense, I think, in the next 2 or 3 videos. But if we were to model the whole plot, so notice this one here, it's actually all associated with level 1 of factor A, but there's several whole plots in here. And if we just model the whole plots, they each get a 1, and then the next one, they get a 1, and then all the way down to the last one, all of those get a 1. And these are indicators which whole plot we're in. And then the same way here. These are all 1s because we're in the same whole plot. All the way down to the last one, we're in the same whole plot. So if we were to model the whole plot, this is what the design matrix would be. So it's modeling the whole plot. And there's T times R. T is the number of treatments. R is the number of replicates within, for each treatment level. Okay. And this will become so important later on. Now, here we can generically call this X1, this piece here, these two, and then this is X2. And so the column space is actually the addition of these two column spaces. Now, this one here, what's interesting is it's actually a larger subspace than X1. And so X1 is actually a subspace, or of the column space of XW. Okay, so this is the design matrix for the split plot completely randomized design. Now the split plot randomized complete block design, that means in our first randomization of the first factor, the whole plot factor, we're doing in a randomized complete block design. So we have blocks, and then within that blocks we sprinkle each one of the levels of the factor. All right. So if we were to look at this model here, and you go back, and it looks exactly like a randomized complete block design. And the reason it looks like it, because it is. That's exactly what it is. And now this second one is also, it's a randomized complete block design within each of those whole plots, but it's this. So we get a gamma associated with the second factor, and then the interaction terms between the treatment and this second factor. Treatment 1 and treatment 2, or factor A and factor B. And of course the errors associated with. And everything else is the same. These are often put together in one error term. The whole plot errors normally distributed. The split plot errors, normally distributed. They're independent. And then this epsilon is actually the addition of those two. Generically, we can write it the same. Y is equal to x beta star plus epsilon, where epsilon's multivariate normal, mean vector 0, sigma squared v covariance. And actually, the split plot's part of what's called a cluster model design, which we may or may not cover. In matrix form, so we have a vector of 1s, column space associated with the first factor, column space associated with the blocks, second factor, and then the interaction between the factors. And so it's very similar. So this model actually looks exactly like the second one, but we're adding this space right here associated with the blocks. So within each of these, in the first design, completely randomized design, they were just replicates. We replicated them each time. But here they're associated with a block. So we model it, and then we can actually split that variability out, making our test more sensitive. And that's one advantage of a randomized complete block design. So otherwise, it's the same. And actually, the whole plot, if we were to model the whole plot, it's the same. And to me, this is a subtlety. If we look at just xt and x, or x alpha and x beta, that's these column spaces. I didn't write it for some reason, but you can tell that this. So like we go down, and we're here, and then when we're still in here, and we move over a column, and we do the same thing here. And each time we move over a column, we move over a column here. But then when we get to the next one, the beta, then it goes to block 1, and right, because we have level 1 in block 1, and we'll have a level 2 of the first factor in block 1, and we'll have a teeth level in block 1. So that's why these are repeated. But each time we get new parameters over here, and actually that is the interaction. So even though we're modeling the whole plot here, it's actually equivalent to the interaction between alpha and beta. And so even though we call it XW, it actually could be called X alpha beta. It's the interaction. It's the interaction space. And the same, these two, these three column spaces we'll call X1. This is X2. The whole column space, of course, is the addition of these two. And X1 is again a subspace of the column space of XW, or the interaction space between alpha and beta. XW is technically not part of the design matrix, but it is needed for establishing the whole plot error, and it's used in tests and contrasts, and it becomes so important. And actually, one of the tricky parts about split plot design is establishing the different types of errors associated with it, and then making sure that you use the right one for the right test. So if your test is too generic, which actually involves both of these column spaces, there isn't an appropriate test. So if you can restrict it to only, say, this subspace, then you can use the error associated with this column space. Or if you could restrict the model only to this part of the design matrix or column space, then you would use the errors associated with it. Anyway, but more on that as we go. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.